Hey guys, welcome back to another episode of Introduction to Computer Networks. This is Polly streaming live again from NTU. And hi Cheng'en, hi Boyao. Good day all of you. Okay, it's really nice weather today and I guess we are finally into spring and maybe close to summer already. Okay. Hi Zhuxun. Good, so let's do the first thing first. This is week 7, episode 11. And the assignments due this Saturday are PA4, quiz 15 to 18. Straightforward. All of the quizzes are straightforward. PA4, I know that several of you have already completed. Good for you. Okay. By the way, PA4 is the hardest one. Okay, throughout all the PAs this semester. If you pass this one, you're safe the rest of the semester in terms of PAs. And hey, we have more. So, hi Yongyi, Qingying. Oops, I must have logged into the wrong account. Hey, glad that I managed to associate you to Heather Xie Hanzhen. And Nico. And Idris No Limit. Cool. And Yanjia. Okay, welcome back. You know what? The topics today are also straightforward. Okay, just 3. All of them are about video applications, or also known as multimedia services. Okay. So, by the way, transmitting video on the internet is also called video streaming, because a video is a sequence of these image frames. Okay, and so transmitting these stream of images continuously over the internet is, in action streaming. Okay, so in this first video, you will hear Polly calling video transmission video streaming, and Polly describing it's very challenging to stream video over the internet, and the solution used commonly today is called CDN, Content Distribution Network. 2.6, video streaming and CDNs. Video streaming, the term is very simple. Okay, YouTube, Netflix, Hulu, and Kankan, they're all video streaming services. So what they do is essentially stream videos to you. Now, what is less heard of is this term, CDNs, Content Distribution Networks. You probably heard me talking about these networks a little bit when I was talking about the internet structure. Right? So there's backbone of the internet, there's ISP, and there's end users. But there's also these global service providers. Content distribution network is one of these global service providers, such as Google. Right? So one of the oldest CDN company is called the Akamai. Nowadays, we do have these cloud service providers, Azure, AWS, okay, also in the market for competition to provide content distribution network services. So in a way, the video streaming services such as YouTube is actually the subscriber of the CDN services. So video streaming services high up, very close to the user, and indirect interaction with the user. The CDN is one, half layer below, although still in the application layer, but half layer below, right underneath the video streaming services. Now, in order to explain why video streaming services these days uses CDNs, I'll have to share first how hard it is to provide video streaming services. Let's look at the video traffic coming out of major services such as Netflix and YouTube. So this is according to US residential ISPs statistics. 70% of the traffic coming downlink to the household from Netflix, 60% from YouTube. So just these 2 video services together is already more than 50% of the downlink traffic. So you see, video, a major consumer of the internet now. And this is mainly because of the number of users we have on each of these video services and the demand. Okay, so the number is still growing, demand is also rising. So we see challenges ahead. And the first major challenge is the scale. So that is related to the demand. As the number of users increase and as the number of video demands increase. So when we have users at that scale, Can you imagine serving all the videos using just one single server? If you recall, when we were talking about the hierarchy in DNS, the domain name system, we are only serving what? Host to IP mapping. That is actually very, very short messages. But now we're serving videos. Even serving short messages like what DNS is doing, we need a what? A distributed system. So you can imagine that a single mega video is not going to work. The second issue is also this. Hey, because we have so many users, and these users could be like Polly sitting right here using a desktop and connected to the wired network. But it could be, some of you guys out there, still taking the metro. You might be connected to the internet using 4G, and you are moving around. So the connectivity and the internet access, you can imagine, me and a metro commuter will be very different. You cannot be sending a high-quality video stream to such a user on metro and moving around. But hey, send me, I can actually take high-quality video, but send me a low-quality video. I mean, neither of us will be happy. All right, so we do have this other challenge here, heterogeneity. Different users will actually demand different qualities because we have different capabilities. Some of us are stationary, some of us are mobile. Some of us has a lot of bandwidth to download videos, but some of us don't. All right, so to address the demand, to address the heterogeneity, okay, in these users, solution is to use CDN, which is a distributed application level infrastructure. We'll definitely talk about CDN more later. All right, now we have the two terms established. Next, we will talk about the video a little bit more. Okay, as you heard, Polly said that a video is a stream of image frames. Inside each frame, it's a two-dimensional pixels of colors. And we'll need to use a certain number of bits to represent these colors. The more bits we use, the more vivid the colors are. Okay, so altogether, you can imagine to represent a video, we use lots of bits. Okay, so in this video coming next, you will hear again the nature of the video, and you will also hear these video encoding scheme, video codecs, that try to compress the video such that the number of bits we use to represent the video will be as low as possible. Therefore, the amount of bandwidth requirement to send the video will be as low as possible. And therefore, users of the videos will be happier, okay, with a higher chance. Now let's talk about the video a little bit more. This is the content we're distributing there. Originally, it was an analog signal. It's a sequence of images that we are displaying, okay? And the display is at a constant rate. That means at every time unit, you take a snapshot of what it looks like right now. Okay, so therefore, at a constant rate, a sequences of these images. So, for example, we take 24 images per second. So that is what the cameras are doing, taking images continuously, right? So Polly right now is sending 30 images per second, or sometimes it's also called 30 frames per second. Your display, okay, will be displaying 30 images per second as well. Now, 30 images per second is actually pretty low. Therefore, from time to time, you see Polly's action is a little bit, awkward, not exactly smooth. These days, in order to make sure that you have very, very smooth motion, 60 frames per second is the way to go. But hey, sending 60 images per second versus 30 images per second, that is at least, okay, twice the amount of traffic. So you see a little bit of trade-off there. If we want very high video quality, that also usually imply higher bandwidth requirement. And the digitalization process is this. So every second we take a certain number of images, and within each image, we divide the image into discrete number of these pixels. So you see each of these red dots is a pixel. Okay? And for each pixel, we use a limited number of bits to represent the color. Okay? So usually the intensity of the red color, intensity of the blue component, intensity of the green component. Now because the number of bits is limited, so that you actually approximate, okay, the actual intensity to some quantile. So this is also called the quantization process, digitalization or quantization process. Now, coding. So provided all these bits being generated, the next thing we do is to just simply send it. Okay, how about that? Well, that was actually what we were doing maybe a couple decades ago. Okay, but nowadays we add compression mechanisms or coding mechanisms. All right, so compression, coding. Compression is more specific, meant that we would reduce the number of bits we need to transmit, reduce the number of bits we need to store for the same content. But coding usually is more general, okay, not necessarily reducing the size, sometimes increasing the size for the purpose of trying to recover from errors. Okay, so coding is a little bit more general. It's just that when we're talking about coding videos, it's usually just compressing videos. And we're exploiting, okay, redundancy that is natural in the content. So redundancy could exist here, okay, within one frame, within one image. You see here, the sky, all these pixels in the sky, they would actually look very much the same. The colors are pretty much the same, right? So that is called a spatial coding. Okay, so instead of sending all the values one by one, okay, how about sending only two values? The color and the number of times the pixel, the color is going to repeat. Okay? So two numbers instead of n numbers. That reduces the number of bits we need to transmit. Okay. The other way, so that was spatial. The other way is temporal. So that is to look at this from one frame to another frame when we're in action. Okay. For most cases, slow action, you will see that frame I and the next one, I+1, there's not going to be much difference. So, hey, these pixels remain similar here. The colors pretty much stay the same, right? So why don't we, instead of sending all the pixels in a frame, okay, send only the differences from the new frame to the old frame, right? So if we take a subtraction, okay, newer frame subtracting the older frame, then you get, very little differences. Most of the pixel differences are probably just zero. Then it's much easier to send a whole bunch of zeros, which you could use just zero and the number of times the zero repeated itself. Okay, so a combination of spatial and temporal redundancy exploitations. And the coding schemes, the really old one, those that are decades ago, are the constant bitrate coding. Because what? The number of bits is fixed to represent each pixel, and the number of pixels is fixed per image, and the number of images you take per second is also fixed. Therefore, the number of bits you're sending out is also fixed. Nowadays, the coding is variable bitrate. So it really depends on the amount of spatial and temporal redundancy you can exploit. Those movies with really fast actions, then you don't get very good compression rate because the from frame I and frame I+1 usually large, so you don't get to save too much. As a result, the bit stream you send out is in different bit rate. Okay, so lots of actions, high bit rate. Not much motion, low bit rate. So examples. This is MPEG version 1, MPEG version 2, MPEG version 4. And you see in the older version, the encoding rate is much higher. Okay. Nowadays, using MPEG-4, the suffix of the file names of MPEG-4 video is usually just this, MP4, something.mp4. Compression rate is really good, so we could send very high quality video under 1 megabits per second. Now, yeah, you see version 2 seems to be requiring more bandwidth. That's because it's in DVD quality. The number of pixels that you're sampling is way higher. Okay, so CD-ROM is actually pretty old, as I said, a decade ago, and maybe a couple decades ago. All right, next is the first protocol we're introduced to stream video. It's called Dash. It's used very commonly to stream store video. So store video is among the 3 types of video streaming services we'll be using. So in this video coming up, Polly will explain what streaming store video meant and introduces Dash, the protocol. And by the way, guys, pay attention to this video because quiz 15 is coming right up. Streaming store video. This is among the most used video streaming services in the world right now. So there's live video. There's also interactive video. Those are actually harder to do. We're not going to talk about those services. If you're curious, please feel free to dig into chapter 7 textbook. But as an introduction in chapter 2, we just talk about this one here, the stored video. This is also the video on demand service that Polly mentioned slightly earlier. The service model, hey, surprise, surprise, client server based. So the server being where the videos are stored, okay, and the client is the consumer of the video. Okay, quite straightforward. And streaming is just to pull the video frames one by one across time. And the first protocol that I'll be introducing is called the DASH, Dynamic Adaptive Streaming over HTTP. So from here, you see that this is what video streaming over HTTP and over, therefore, TCP. So unlike what we have expected probably, right? Video services does have high bandwidth requirement and short delay requirement, but TCP, how would it serve? Okay, well, for video streaming services. Well, the main reason will be explained the next topic called CDN. Here, what we are addressing is this. Between the client and the server, there's the internet. Okay, internet fluctuates a lot if you think about it, right? People come and go, sending other video traffic, sending other big file download traffic. Now, these is gonna, interact with each other, and therefore the available bandwidth really between the client and the server is varying a lot over time. So dash here is to try to adapt, okay, to the internet conditions. That is very dynamic. All right. So the main intelligence is actually at the client side. Okay. What server did is just to prepare such that the client can be intelligent about, okay, about streaming video over the internet. So what the server is preparing is doing this. Video files are usually large, and it's usually many frames being played or being transmitted over time. And so what the server did first is to divide the video files into shorter segments. Okay. So here in the site, we call it chunks, video chunks. A little bit like in P2P, BitTorrent actually cut big files into what chunks. And each chunk is stored and encoded in different rates. If you recall when we were talking about videos, right? Depending on how much detail you want to keep in the video, depending on the quality of the video you want to be able to play back, you might want to encode it at different rates. Okay? Higher rate usually meant that more detail, better quality. Lower rate usually meant less detail, lower quality. But the trade-off is, hey, for high quality video, you do need a bit more network bandwidth to transmit. But for lower rate video streams, there's less need of bandwidth. Okay, chances higher that you don't run into trouble sending a low rate video stream over the internet, right? So, well, to allow these, flexibility, okay, depending on how the client senses what the current network bandwidth is, the server is actually storing each chunk and encoding multiple versions of these chunks at different rates. So when the quality, when the network bandwidth is good, then we could download a higher quality video, a higher rate video. When the network bandwidth is not sufficient, we'll have to drop to a lower rate, okay, version of a chunk. Now, what's being communicated to the client from the server is this, the manifest file, which is providing the location, the address of all these different chunks at different rates. All right. Now, the client. What the client does is periodically measure the client to server or server to client bandwidth. Okay, so what it means here is exactly the available bandwidth. Right. And then, provided this bandwidth limit, consult with the manifest file and then request the chunk, okay, the client is looking for at the time, and chooses the maximum rate such that it's under the bandwidth limit. Okay, so measure periodically the available bandwidth, pick the version of the chunk such that the rate is right below the limit. And at different point in time, so periodically, the client does the measurement of the available bandwidth. If it gets back up again, then you pick a rate that's a little bit better. Okay. Otherwise, if the available bandwidth drops, pick the rate that is a little bit lower. Right? So you choose different coding rate depending on what the available bandwidth is at a given point in time. And that takes us to quiz 15. Yeah. So let me go to the whiteboard so I can dribble. So MP4 is an encoding scheme. You know what? H.264 is by far the most popular one. So according to the scheme and according to Google, if we encode a video at this resolution, the bandwidth requirement is about 16 megabits per second. Okay, a slightly lower resolution, lower bandwidth requirement, and so on and so forth. Okay, so given this table on the left, I ask, which resolution would the Dash client choose under different available bandwidths? Q1, if the available bandwidth is 10 megabits per second. Q2, if the available bandwidth is 3 megabits per second. All right, so very straightforward. Let's go to, let's go to channel W7, quiz 15. Hey guys, this channel is in quiz part 2 because now we are in the second third of the semester. Guys, type up your solution. You have only 2 minutes. Okay, we'll take the fast and correct responder for bonus, and we'll probably take more, okay, this time. All right, so 2 minutes only. Oh, okay, too fast. Okay, you guys are all within a minute. Yeah, I thought that it's not gonna be fair if we just take the top 3. Yeah. Great, guys, hurry up. Very good, Yuting. Yeah, you're probably thinking, it takes more time to type things up, right? But by the speed you guys uploading the solution, I felt that, hey, you guys pick up what Dash does, right? Available bandwidth, pick the encoding rate that is right below the available bandwidth. Exactly. Okay, Team 4 Zhu Xun here says 2K because 2K is exactly 1440p. Great, Noe, there you go. Yeah, I think you guys all answered the question already, so we don't have to wait for 2 minutes. Good, so yeah, that is Dash. Okay, quite straightforward. But in terms of choosing what is the right resolution given the available bandwidth, that is straightforward. There are actually 2 things that a Dash client needs to decide. Okay, so that will be described in the next 2 videos. Here's the first one. So you heard that the client is actually pretty busy. It's measuring the available bandwidth and deciding what is the best rate of the chunk to download. So bandwidth, higher rate, or lower rate. So this is one of the intelligence the Dash client exercises. There are actually 2 more intelligences that are implemented in the client. The second one is this, where to request the chunk. And the third, when to request the chunk. Let's talk about each of these a bit further next. Where to request the chunk. What happened there is that in the manifest, there could be multiple URLs indicating that there are multiple servers carrying that particular chunk at that particular rate the client is looking for. Now, among many of these physical servers offering the same chunk, same rate, the client needs to pick one of these. Okay, so the typical decision is to pick the server that is the closest to the client. By closest, usually people mean the server that is showing the smallest delay back to the client. Now, how do you get the delay from the client to the server and back? Well, the client can send a short ping message, okay, and see how long does it take for the server to answer back, or to send trace route, for example. So clients are also, in the meantime, sending these probes to find out which of these servers will be closer to the client. And this is also done periodically, just like how the network bandwidth is measured. Yeah, so Dash client also tries to find which server is the closest, finding where to request. And last is when to request. In this video, there are 2 key terms, buffer starvation and buffer overflow. And they both sound negative. Make sure that you understand the differences of the 2. When to request the chunk. This is actually the intelligence that is a little bit hard to explain because we did not talk about a very special component in a streaming system. So let's go back a little bit to the architecture. So there's the client side and the server side. At the server here, we have huge hard disks storing video chunks and allowing clients worldwide to pull the video streams down to the internet. First component of these video frames here is the socket, okay, at the client. But then quickly, it enters this thing called the video buffer, okay, or the client-side buffer. So video frames we're getting here first. So the app that the users are playing with is more graphical, okay, and where you see a play button like this. Okay, when we hit play, what happened there is that the client sends a short message to the server that, hey, I'm gonna download this video at this rate, okay, and video frames begin flowing in. All right, so you can think of the buffer like a bucket, and if you think of these video frames as a flow of water, then it will be easier to understand. Right? So usually what happened is here, the client, before we really play back the videos, we keep a number of these frames first. Okay, when there's enough of these, so it's like a reservoir here, the buffer. Okay. Then we begin to pull the frames one by one and then render it on the player. Okay, so the time you hit the play button until the time the first frame begins playing, that is called the buffering delay, okay, or the startup delay of these stored video streaming services. All right. Now, the reason that we actually store a number of these frames before playing back is exactly because of this. Usually the playback rate is constant. So for example, 60 frames per second. So this is usually to ensure a smooth experience. Right? So viewers will all prefer a higher frame rate if possible. Okay. Now let's say that, hey, we're going for 60 frames per second rate, but the network bandwidth here suddenly goes really bad. Okay. What's occurring here at the buffer space is this. Well, we're fetching still 1 frame per second. Okay, 60 frames per second. That is, oops, sorry. So 1 frame per 1/60th of a second. But the thing is that the network bandwidth goes down. The incoming rate of the frames will be much lower, and it will not take much time until what? We see the buffer space emptied up real quick, and eventually there's no more frame in the buffer. Okay, that is called the buffer starvation. The buffer is starving of the video frames. Is that good? It's actually not good. What happens here is you're seeing your screen smoothly playing video frames one by one, but suddenly what? It freezes. Okay, so that is called an interruption. So that's very disturbing to the viewing experience. Not good. So the client usually sends back another message to the server saying that, hey, you know what? The network situation is not good. How about that I download another version of the video such that the rate is lower? Okay, I'm okay with the lower quality because otherwise I will not be able to sustain the frame rate I was looking for. Okay, so usually you'll be automatically switched down to a lower resolution, okay, or a lower frame rate, for example, just to ensure smooth playing back of the video frames. Okay, so when to request chunks so that the buffer starvation does not occur. Right? And let me make sure this is clear. Right? So that message from the client to the server asking video chunks being sent with a lower rate version, that should occur before actual starvation occurred. Now, as to how much earlier, that is the intelligence the client needs to decide. Right? So Dash allows the client to implement different strategies to decide when to start changing the rate, okay, automatically according to the network bandwidth to avoid buffer starvation. Now the other situation is this. The client also needs to decide when to send back a message to the server such that the buffer does not overflow. So this is the other way around when the incoming rate here is really nice. But the server here, the client over here, the user over here at the client is what? Hitting a pause button, for example. Taking a restroom break. When this happens, right, the player will not be fetching frames one by one as usual. And quickly what? Hey, the buffer space is also limited. We have a buffer overflow situation. All the subsequent frames coming in here will get what? Dropped. So this is just like in the router. We have the buffer space for the packets. Now, in case the outgoing rate is too slow and incoming rate is too high, we have what? Packet drops. Similarly, if the user is hitting pause or doing something else, then we might have a buffer overflow situation. This is not good either. We definitely do not want to miss frames in the middle of video playback. So clients, therefore, send back a message to the server, asking the server to hold. Okay, now stop sending the frames until I tell you so next. So this is also another intelligence the client side implements, telling back the server now to stop and hold the sending of the frames. All right, so generally, too little frames, too many frames, neither case is good. Okay, so neither case is troublesome. All right, now the last topic, CDN. So in this video coming up, you'll hear Polly explaining more that using one server to serve video is just not gonna scale. And so we need CDN. And this video is a little bit long, over 7 minutes, is because Polly will also be introducing the two flavors of building a CDN. Now between the two flavors, one of them is cheaper to build and easier to maintain. Okay, so guys, you want to pay attention because right after the video, Polly is going to take a poll, okay, and you will tell me which one of these two flavors you feel it's cheaper to build and easier to maintain. CDNs, content distribution networks. This is the part in video streaming services Polly finds the most amusing. Some of you might know, many of the global services that are popular worldwide uses some sort of CDN in the back. So that includes Gmail, Dropbox, even the Zoom teleconferencing system that is a bit controversial these days. The reason for that is this. You hear a little bit back, Dash. Okay, so Dash there is nice. The client can actually adapt. Given this much network resource, we ask for the video chunks and the version that's just behind, okay, just below the available bandwidth. Okay, so this adapts to fluctuations on the internet, which includes when the number of users increases, yeah, the remaining available bandwidth will be lower and lower. The Dash there does is just to adapt to the change. The thing is that the change could become unbearable. So if the number of users increase continuously, okay, and if a high number of them are demanding a service simultaneously, you could end up with available bandwidth that is so low, it's not even sufficient to serve the chunk with the minimum rate. And to deal with the network capacity issue is what CDN here is mainly to address for. Again, there's a critical issue on popular systems on the internet today, the scalability issue. Okay. And CDN here magically addresses some aspects of these scalability issues. Let's step back a little bit and look at option 1. So this is to contrast CDN, and this is the simple, naive solution. What about using just one server? Yeah. If you recall when we were discussing DNS system, the name IP address mapping service, we were saying that originally there's only one server instead of having a distributed service, isn't it? Yeah, using one server, we have issue like this, single point of failure. That server down, the entire service down. The mega server down, the video streaming service is also down. And that one server there is also the point of congestion because everyone is asking for its service. And there'll be part of the world being happy because they are close to the server, but there will be the rest of the world will be unhappy because they are farther away from the server. And delay long is not good, and there's also a fairness issue, isn't it? How come you always get to enjoy short delay service, and how come, okay, I always have to wait? And last, this one is more distinctive in video streaming service. In DNS, the name to IP mapping are all short messages. But here, for video streaming, it's continuous, and each frame is already bigger than the name IP mapping. So we're sending these streams repeatedly, and some of the streams are probably the same. So users might be requesting popular videos, which means we are sending multiple copies of the same video over and over again. Right? Now, not a very thrifty way of using the network resource. Solution like this, definitely not scale. This is very clear. And that takes us to option 2, which is exactly what CDN is doing. That's, instead of using just one physical machine storing one copy of these content, that's use multiple machines storing multiple copies of these content. And more importantly, okay, distribute them around the internet, making sure that they are very widespread geographically. And the point of doing this is so that, hey, if there's a server here, the clients around it will be able to communicate and get the content within the local area. Therefore, the network capacity, other than this part, can be opened up for other clients interacting with other servers. Okay, so the number of duplicate video transmission can be reduced. A more efficient way, a more thrifty way of utilizing the network resource. Now, let's talk about the two models the CDNs are architecting their physical infrastructure. First one is called the enter deep. Okay, so this is actually speaking that the infrastructure, the machines themselves, okay, for storing these videos are actually deep, closer to the end customers, deep into the ISPs, to the local ISPs, so that they are close to the end customers. Akamai, one of the oldest companies, is implementing exactly this architecture. Therefore, there are so many locations around, okay, in Akamai. Pretty much for each local ISPs, Akamai probably set up a site where you see typically a rack of workstations, and they are redundantly connected to other machines in the access network, other routers in the access network, and potentially very close to the users. So Akamai there, when they deal with an ISP, they rent for the rack space, they rent sometimes for physical machines on the rack. They definitely subscribe to the connectivities provided by the local area access networks. Now, the other model is bring home model. Okay, so by bring home, these CDN architecture is to say that the physical infrastructure, the servers, okay, they're storing video contents are actually closer to the service home, where the origin of the video sources are from. Essentially, the company generating the video. Right? So it's actually closer to the home company. Therefore, they are actually higher up in the internet hierarchy, closer to the core instead of to the local access network. Okay, so they are actually very close to these POPs, the internet exchange points. So the idea is that such a CDN company will build up a few racks of these workstations and just connect to the POPs where they get access to the rest of the internet. Right? Now, because the number of locations is very limited as number of POPs are also limited, so there are not many of these sites. And the sites tend to be bigger. Instead of calling them sites, they are called clusters. Okay, so the physical infrastructures will be formed by server clusters. Okay, few of these clusters interconnected through the POPs, the internet exchange points. So they did not go deep into the access networks. Limelight, this is a cheaper CDN service, offers bring home CDNs. Now, so you see a little bit also advantages and disadvantages of the two models. This, closer to the end customer, some big wealthy service providers might subscribe to this because potentially maintaining the infrastructure is very high cost. Now, those smaller service or smaller content providers, not quite as wealthy, then might subscribe to a bring home CDN service. Alright, so guys, enter deep versus bring home, which one will be cheaper? Okay, type it up on the chat. Okay, just take one. Let's see. Uh-oh. Guys, we're taking a poll. Oh, there. Okay. Bring home? Predominantly bring home. Hey, guys. Hey, I see that many of you are paying attention. Great. Well, at least the first few. Ryan, great job. You're paying attention. And Junhuan too. Okay. Yeah, very good to know. Yeah, you hear the keyword, right? Limelight, cheaper. Akamai, a lot more expensive if you subscribe to their CDN. Yes. Needed fewer. Yeah, exactly. Because in Bring Home, only like tens of clusters. Okay, fewer number of these sites. Limelight needs to maintain, so they are cheaper. Great, great. Yuling, you are actually trying to provide the answer after thinking and providing an argument of your choice. Very good, guys. So that is CDN, 2 flavors. Next video, you will see an illustration of how when a client is looking for a video, a request will be sent to the origin server, but the origin server on CDN will not be sending the video because the origin server cannot be the single server. That's the bottleneck of everything. So there's a CDN, a network of servers. So the server will reply, the origin server will reply to the client and direct the client to go to a nearby server. So that is the first part of the next video, an illustrative example. Second part, you see that the CDN together with the client and the server, they are a network itself at the application level. They are sitting on top of the internet infrastructure. Okay, it's over the top of the internet. So there's a term called OTT service, over the top service, that actually meant CDN type of applications. Okay, and nowadays, how you manage such a OTT service is a hot research topic because it concerns how satisfied your users will be and how much cost you can lower from the provider's point of view. Okay, so next video, OTT. And let me illustrate how the content consumer or the client, content provider, the origin server, as well as the CDN. Okay, CDN is the one distributing the content, how the 3 components interact. And I'm going to use Netflix as an example. All right, so client here will be retrieving a video, and origin server here, the content provider, Netflix over here. So CDNs, the content distribution network that Netflix subscribes to, will be allocating a number of physical machines worldwide, okay, and stores copies of the content. All right, good. Okay, so the motion is this. Okay, a customer turned up, okay, and decided to watch Mehmet, the movie. Okay, so the user here is obviously a subscriber of Netflix, then it would send the request to Netflix. And Netflix will then send back a manifest file telling the subscriber where the copy of the video is stored. So this guy, this guy, this guy, this, all 7 of them will be reported to the client, to the subscriber. And subscriber then will pick one of them. Okay, so redirected to the nearby CDN to retrieve the content. Now what's nice about having CDN is not just the content therefore is closer to the client, it's also to address this issue. If the network goes bad here, okay, from the first CDN, the client there can choose a different CDN where the network congestion is lighter and go this way. And CDN working this way is also called a over-the-top service. Allow me to explain. And it's better explained illustrating it this way. So let's bring all these entities involved in a CDN service high up, like this. Okay, so you see there's a separation of the internet physical structure and the OTT service. So these CDN servers, as well as the original server, as well as the client, they form a network. It's a service network. It's a network formed by what? Hosts only. Now let's abstract away the infrastructure here using just a channel. Okay, so you see here high up, this is a network. And CDN, you can think of it as a service provided to the content provider such that we enable end-to-end or host-to-host communication. So it works like there's a network at the application layer. Now, maintaining such a network such that it works very efficiently distributing content is not easy. There are a lot of key design challenges. Okay, One is, hey, as we mentioned earlier in the example, right? The client will then select a nearby CDN node to retrieve the content. Okay, that is usually because the delay will be shorter, and the segment of internet involving the communication is short as well. Therefore, less chance of other traffic interfering with this one. But how do you know a shorter delay one is certainly the one that uses the shortest segment to travel? How? And maybe you want to use a combination of short segment and short delay. So, yeah, exactly how you design selecting of the CDN node, that selection algorithm, that is something to be investigated about. Okay. Second, in the presence of congestion, well, congestion comes in very light level, sometimes very heavy level. Would viewers be really unhappy about a certain level of congestion? It might really depend. Okay. So how do you know when to switch from one CDN node to another one? Yeah, that is another challenge. Okay. So one could come up with algorithms that switch ahead of time before it goes really bad, or switch right at the point that's needed. Okay. You see that each of these strategies may carry certain advantages and disadvantages over one another. And last, wow, at the beginning, right, we said that CDN would choose a number of physical machines and maintain duplicate copies of a certain video. But which machine? And which video? Yeah. So this really has a lot to do with resource allocation and where the demands are. You want to make sure that the content is pushed closer to the demand, but you cannot be copying all the content, right, to every CDN node. So how do you conserve? Again, challenging problem. If you're curious, definitely read more into chapter 7. All right, so you see, OTT, it's a big can of worms. Okay, if you want to keep the number of servers as low as possible for the provider, and yet making sure as many users will be happy, very challenging to do. And yeah, so there was a very interesting question from Hanjin during the video playing. So why is bring home, guys? This is because the people defining these two terms, bring home, enter deep, are the people designing the internet. So these people designing the internet are thinking from the core's point of view. Okay, so the core of the internet is home. Now we as end customers will be thinking, hey, we are home, right? So it's a little bit counterintuitive. Bring home meant that it's home to the core. Deep into the woods, yeah, far away, those are end customers. Okay, so the designers are in the core, and the users, the enemies, are actually out there. The monsters are out in the woods. Hey, I'm not trying to generate a controversy here, but it's a perspective. Okay, bring home to the core, enter deep to the edge. Now, last video, it's not long, but we're gonna run over a little bit. It's just 2 examples of how we implement the redirection you saw in the example on the internet. First implementation borrows from DNS. The second implementation is simply that when the client is asking for a video, the server replies the URL, okay, pointing to exactly where the video is. Okay, what's remaining are just 2 examples of how CDN requests are being redirected such that it reaches the physical location. So in the first example, it's more the Akamai model, which borrows from the services provided by DNS. So example goes like this. Bob requests a video from cinema.com, and this is the video ID. Okay, so browser here, browse around and decided, and Bob here hits this link. But the thing is that that video is actually stored here physically. The King CDN, a CDN company. And so it's stored on kingcdn.com's web servers, this location. But what happens here is, well, Bob's browser actually sees this is the host to contact. So first thing first, ask the local DNS server for the IP address of this guy. Right? So resolve this guy. Bob's DNS server there will what? Check cache. If not a hit, go to the TLD server. TLD server will share what is netcinema.com's authoritative DNS server. And so Bob can direct the query to the authoritative DNS server for the IP addresses of netcinema.com. But what's really curious here is the authoritative DNS server of netcinema.com, instead of returning an IP address, it returns the redirected path. Okay. At this point, Bob's local DNS then resolve for this name instead. Okay. And so check the cache, check with the TLD server, and eventually reaching the King CDN's authoritative DNS server. That query goes, and finally now, King CDN authoritative DNS server will return the IP address of kingcdn.com. Okay, so IP address of this guy acquired, and step 5 sends that IP address back to Bob's web browser. From there, Bob's browser can fetch the video from the actual location of the video. Right, so this is redirecting the client to the copy through the DNS service. In example 2, the content provider here only needs to do the minimum, which is to provide the logging service. So Bob here as a subscriber just logging first. Okay, that's step 1. And quickly, Bob is redirected to the CDN. And in Netflix's case, Amazon's cloud is the CDN. So Bob here will be browsing what videos there are available, okay, and ratings and how long the videos are from the web servers Amazon has already set up. Now, once Bob has decided on watching a video, then step 3, the manifest file of that video is returned back to Bob. And Bob will begin to fetch the video from the physical machine Amazon has set up to store that particular video, and somewhat close to Bob. Last is just that the CDN server begin to dash over HTTP streaming the video. Now if we compare the two models a little bit more, we see that in the first model, the content provider has slightly better control of where the redirections should go. But in the second case, the redirection is all done by Amazon. So there's not much Netflix needs to do, or not much Netflix can do. So it's more a trade-off between control and work. Okay, so more control, more work, less control, but less work. So, well, as a content provider, you'll have to decide for yourself. All right, so that's the last bit of CDN, and that's also all for today. Tomorrow, hey, hot topics coming. We'll start chapter 3, the transport layer. Okay, so the topics there will be just as interesting as the topic today. As you see the course material progress, there will be more technical content, and for guys coming from the tech background, we'll find these next topics more and more interesting. All right, so I'll see you tomorrow morning, and thank you for the attention, and I say goodbye. Bye. Yeah, sorry that we have to run over the time a little bit. This way we can start fresh, chapter 3 tomorrow. Bye. Enjoy the weather.